Hello student to the foundation of classical electrodynamics course. So, today we will going to learn the delta function which is under module 1. So, today we have class number 16. So, we will start a very important topic today, which is delta function. So, in 1D, say 1D, in one dimension the delta function is mathematically defined in this way: a function which is 0 when x is equal to 0 and this function goes to infinity when x tends to 0 or here when x is not equal to 0, and here in other cases when x is equal to 0, this function goes to infinity. Not only that, we have another very important property, that if I integrate this function over the entire x axis, because we are taking one dimension, then this value is 1. Okay, this value is 1. So, this is the property of the delta function. This is the way delta function is defined, that this function delta x should be 0 when x is not equal to 0. When x equal to 0, this delta function delta x should tends to infinity, but if I integrate this function over entire space or over entire x axis, then the resultant value should be 1. So, here also you should, from here we clearly understand one thing: the delta function should have a dimension 1 divided by length, at least in one dimension. Then only it should be dimensionless by multiplying dx, and at the end of the day whatever we get is simply a number. So, that you just try to understand from this expression. This is a very important expression. Now, if I visualize this function, how it look like? Suppose this is my x axis and this is at x equal to 0 point. And now, if I plot my delta function here, it is 0 here, it is 0 over here, and suddenly it shoot up going to a very high value, and this is roughly the structure of the delta function. It goes in principle it should go to infinity. So, this is the delta function that we are talking about, and this should be the distribution. Well, if I make these things in a general way, it is not necessarily that always we have the delta function x equal to 0. We can shift our coordinate, and if I shift our coordinate to some other point, suppose this is my x and this point I am talking about, this point which is x equal to a. So, now my delta function is defined like delta x minus a coordinate shift. So, same thing happen here, all the values will be 0 and suddenly we have a huge steep here, and then it goes to 0 for other values. In this case, this quantity should be 0 when x is not equal to a, and this function delta x minus a tends to infinity when x is equal to a, and if I integrate this quantity minus infinity to infinity delta x minus a dx in one dimension, then this value gives me the value 1, okay, like before, but this is a general form where we are making a coordinate shift. Okay. Another very important property, so these properties are very important. Another very important property is this: if I multiply a function with the delta function, then obviously this function when x is not equal to 0. So, for this case this quantity is always 0, and these things will be meaningful only when x equal to 0. So, the function at x equal to 0 delta x, that should be in the right hand side. Try to understand that delta x is in all the point delta x is 0 except x equal to 0. So, only this expression is meaningful at the point when x is equal to 0, because in that case delta function has some meaning, a non-zero value, and that is why this multiplication should be meaningful when the function is evaluated at 0, x equal to 0 point multiplied by delta x. So, that you should understand, or we should realize this. Okay. So, what I am trying to say is this: f x is a continuous function and f x delta x is 0 everywhere, except at point x equal to 0. So, that is why this function is important. The evaluation, this function can be evaluated at x equal to 0, then multiplied by delta x. Now, if this is the case, then we can have an interesting property, and that is this: minus infinity to infinity, if I integrate this quantity f of x, then delta x dx, then what we write in the right hand side, because this quantity I mentioned is meaningful at x equal to 0 when the function meaningful when we evaluate the function at x equal to 0. So, in the right hand side I should simply write integration minus infinity to infinity f evaluated at 0 delta as a function of x and dx. Now, you note that f 0 is a fixed value, it is a constant, it does not depend on x. So, I can take this term outside the integral. So, I should write this and minus infinity to infinity delta x dx. Now, you can see that this quantity again by definition is equal to 1, because I just mentioned that when we integrate this delta function minus infinity to infinity over x axis in one dimensional case, this value gives me 1. So, this is true. So, as this one. So, exploiting that expression here, we can find that this integral value is eventually f0. Okay. So, we have a very interesting expression, and that suggests that if I integrate minus infinity to infinity of any given continuous function, one dimensional function multiplied by delta function dx, then this integration is simplified and we simply have the result this. the value of the function at x equal to 0 point. So, this is a very very interesting and important result, and we should note it. So, this is the result where we can find out the integration involving the delta function for any function. Now, we can generalize this, because this is also true for the coordinate shifting. So, in general, if I write in general, we can have function of x delta x minus a. Now, I am making a coordinate shifting, delta is now defined at x equal to a point, then that quantity should be simply f a delta of x minus a, like before, only I put a in place of 0. Now, if I integrate it minus infinity to infinity, f of x delta x minus a is equal to f of a. So, delta x is a very very important function as far as the integration is concerned. So, any function multiplied by delta function, if I want to integrate over the x axis, in this case, okay, I should put dx here. So, it should be dx. So, this is a very very important result. Okay. So, now we will like to understand quickly that in reality how the delta functions is realized. So, realization of realization of delta function. So, delta function one can realize under certain with putting certain limit of the well known functions, and then one can understand that how how the delta function is physically possible. So, let me give the first example quickly. I will give few examples. So, the first example is this function. Suppose we consider a function of x. These are few standard example, in any book you will going to find this. Function of x, suppose given as 1 by a, and this function is distributed in this way. It is 1 by a when the x value is in between this limit, and 0 otherwise. This is the way the function is defined mathematically. Now, if I plot this function, the plot will be very very simple, that this is my x axis, I have this point is 0, I have a point here a by 2, I have a point here minus a by 2, and when the x value is in between a by 2 and minus a by 2, we have a value, constant value 1 by a. Suppose we have this value 1 by a here, and that means eventually I am having this step kind, this box kind of function, and it is 0 all the others, for all the others value. So, my function is this, from here to here it is 0, suddenly there is a jump, we have a fixed value 1 by a here, then again there is a sudden drop, and then it goes to 0. So, this value is 1 by a, and this is my y axis, and this is x equal to 0 point. Now, one can understand this limit. So, how the delta function is defined for this case? The delta function can be defined for this case in this way. If I take limit a tends to 0 for this function f x, that eventually gives me delta function, and you can understand that. So, a tends to 0 means I will reduce this length from, because a tends to 0. If you reduce this length, this height will gradually increase. So, what kind of figure I will going to get under this limit, I can draw here. It is something like this. Suppose this is my x axis and I start with this a value, this is 0, and my initial function is this form. This value is minus of a by 2, and this value is a by 2, and this value is 1 by a. That was the initial function. Now, I put the limit. I gradually decrease the a in such a way that these things will shrink, and so next point we will get the next, if we reduce that, I will get a function like this, because I am reducing a. In a similar way, if I reduce a more, I will get a function like this. If you reduce a more, I will get a function, very sharp function like this. So, gradually this function will going to shrink, and eventually we will going to get the ideal delta function. An ideal delta function, I already mentioned that it goes to 0 at x equal to 0 point, it goes to infinity at x equal to 0 point and 0 otherwise. So, the ideal delta function is simply this, goes to 0, very sharp increment, and this is the condition. So, this limit, which is the width of this function, which is a, is tends to 0 here, and this is precisely the case for this function. So, this is the way one can realize the delta function, and this is not the only way one can realize delta function. There are other way also. For example, I am just giving one function, and that is this one. So, delta function can also be considered as limit a tends to 0 and then 1 by say mod of a and root over of pi, and then e to the power of minus x divided by a whole square. So, this is typically a Gaussian function having a width 1 by mod of a. So, again if I want to plot this, it looks similar, whatever is drawn here, it looks very similar. When we make our limit a tends to 0, then the function will be something like this, the evolution of the function will be this. So, this is the x equal to 0 point. So, let me draw it. So, this is x axis. So, the initially we have a Gaussian like this for large value of a. Now, if you gradually reduce the value of a, we will going to get a function like this. If you reduce this the value of a more, I will eventually get a function Gaussian distribution like this. So, again you can see that we are gradually tends to a delta function kind of structure under the limit. So, this is the function I am plotting, which is this one, 1 by mod of a, then root over of pi e to the power minus x by a whole square. So, this is a typical Gaussian function, and now I change this limit, I change the value of a. So, under the limit a tends to 0, I am going to get a delta function here. Another example is this. Another example is this, and that is limit n tends to infinity sine of nx divided by pi of x. This is also considered to be a potential delta function, and this is a sinc function. This is related to a sinc function. This function is called sinc function. So, we know that how the sinc function evolves, and again if I draw this sinc function, typically if this is x equal to 0, the typically sinc function is this. This is roughly the figure. So, here we have a peak. Now, if I gradually change, so this is, if I now make this n tends to infinity, then what happened, that I will get more and more sharper this sinc function, and eventually which looks like a delta function. So, this I am just drawing, roughly drawing the condition when this is for when n tends to a very high value, tends to infinity. So, it basically reaches, it basically arrange itself like a delta function. So, this is the way one can realize. So, these are the few examples where one can realize the how delta function can be possible with the usual functional form by exploiting the usual function under certain limit. But the properties are very important for the delta function that we mentioned. Now, we will try to understand few more properties of the delta function, which is very important, and few identities rather. So, the next thing we will understand the delta function identity. So, the first identity is this: if I have a delta function and in the argument I have some constant a and x, then that value is eventually 1 by mod of a and then delta of x. A very interesting looking identity we are having. So, instead of having in argument x, if I have a constant a, then in the right hand side I can write the delta function in its usual form with delta x, but then it should be 1 by mod of a. So, we can prove this. There is a way to prove this, and in order to prove we need to first consider a test function. So, let us take this test function. And this test function is f x, over which we will operate this operator, this function. So, now I want to find out this quantity minus infinity to infinity, our favorite integral f x, but instead of delta I will want to find the integration for this given function delta a x dx. Okay. Now, after that we will make some transformation, like y is equal to x, then x should be equal to y by a, so that dx will be 1 by a dy. Okay. Now, if a is greater than 0, it can be greater than 0 or less than 0, then minus infinity to infinity f of x has now become y by a, and delta y, and then we have 1 by a dy after making this rescaling. So, we will eventually have 1 by a, then integration minus infinity to infinity f of y by a and delta of y dy. Okay. So, that value I know, this condition I know, because this integral is a very famous integral. I have a delta function and function, so it should be evolved at 0 point. So, eventually I will get the result like 1 by a and then f of 0. This is my equation 1. In the similar way, if a is less than 0, that is the another condition we can think of, that now my if a is less than 0, what we have? We have minus infinity to infinity f of y by a and then delta of y 1 by a dy. Now, since we are having a negative, so the limit should be, since a is going to the negative side, the limit should be this one, and in order to make this limit correct, we will simply invent a minus sign, and we should have minus infinity to infinity, because here a is negative means when we make the transformation y is equal to x and a is negative, that means when x tends to infinity, y goes to minus infinity and vice versa. That is why there is a change in the limit under the condition that we are having y is equal to a of x with the condition that a is negative. So, when x tends to infinity, y tends to minus infinity, y goes to minus infinity, and when x tends to plus infinity, y goes to minus infinity, because there is a negative sign carried by this value a. I can fix it by putting another negative sign, and then it simply becomes f of y by a delta of y 1 by a d of y. So, I will get simply I will get minus of 1 by a f of 0, that is the value I am getting, and that is my equation 2. So, now if I tally equation 1 and equation 2, then you can see that for a greater than 0, I have the integration whatever I have minus infinity to infinity f of x and then delta of a x is equal to the value 1 by a f of 0, that value we had. On the other hand, when a is less than 0, I am having minus infinity to infinity f of x, the same integral I am getting. Here we have a dx, ax and dx, that value I get with a negative sign. So, combining these two, because for a positive we have positive, for a negative sign is already there. So, with this note I can write I can simply write this integration minus infinity to infinity f of x delta a x dx is simply 1 by mod of a, because whatever the a you choose, positive or negative, at the end of the day you are getting this result is 0. Now, this quantity, these things I can rewrite in this way. I can rewrite in this way. This I can rewrite minus infinity to infinity function of x, then multiplied by 1 by mod of a, then delta of x dx. I just rewrite this expression in this way. Now, if I tally this side and this side, it simply gives me that this quantity delta a x is simply 1 by mod of a delta x. So, that proves that delta a x is equal to 1 by mod of a delta of x. Okay, this is a very important proof. Okay, next I want to extend this part another identity, but I am not going to prove this identity. So, that identity is this one. So, minus infinity to infinity, if a function we have f x, and instead of having delta function, if I have delta prime, which is a derivative of the delta function, in interesting looking function, it is not a delta function, but derivative of that, this prime suggests it is a derivative, dx is equal to minus of d of f dx, that will be evaluated at x equal to a point. So, the value of this quantity should be this one, and the process is straightforward. So, I am just giving you the hint, and the hint is you just calculate this left hand side integral, you just calculate the left hand side integral with by parts, because this integral left hand side integral, if I want to evaluate, it should be first function f x, make these two function f x, first function f x, and then integration of the second function minus derivative of the first function multiplied by integration of the second function and then whole dx. Now, if I integrate this function, integrate the derivative of the delta function, what we get? Minus infinity to infinity delta prime x minus a dx. If I integrate the derivative of this function, then we simply get back to our delta function with the limit minus infinity to infinity. Now, delta function is meaningful only at x equal to a point by definition. So, at minus infinity and plus infinity, in both the point delta function is 0. So, this quantity is simply 0. Okay. So, eventually I have the first term 0. What about the next term? The next term is this one. It is minus of infinity to infinity, and then I thought that I should not do it, but I am doing it. I can give you other problems, no issue. and then integration of this quantity is simply a delta function, and we have dx. So, this quantity is nothing but again a function associated with the delta function at x equal to a. So, if I now extract this integration, if you do this integration, it should be simply del f del x evaluated as x equal to a point. That should be our result, and that is the thing I just write here. So, I prove it, even though I thought that I should not, but anyway I will give you other problems also. There are ample amounts of problem. Now, before concluding, I like to show a very important identity, and that identity is this one. So, we already mentioned that delta x, let me write it, is equal to limit n tends to infinity and then sine then n x divided by pi of x. So, that is the way one can define delta function. Now, the question is, if I want to find out this quantity, this integral, what should be the value? The integral is minus infinity to infinity e to the power of I k x dx, a very important integration, and the question is what should be the value of this integration. So, this integration we will do in this way. So, let define n in such a way that n tends to infinity, and integration minus n to n e to the power of I k x dx, right. So, this quantity is how much? Limit n tends to infinity e to the power I k x divided by I of x evaluated at minus n and plus n. So, this quantity is limit n tends to infinity e to the power of I n x minus e to the power of minus I n x divided by I over x. Then limit n tends to infinity, this quantity is 2 I sine of n x divided by I x, this I will cancel out, and eventually we have a term like 2 of pi, I put another pi, limit n tends to infinity and then sine n x divided by x. So, this quantity pi x, because I put another pi. So, you can see that this quantity is nothing but my delta function x. So, eventually I get minus infinity to infinity e to the power of I k x dx is equal to 2 pi of a delta x. This is a very important result. In general, I can write it, delta at x minus x prime is equal to 1 by 2 pi integration minus infinity to infinity e to the power of I k x minus x prime and then d of k. So, this is a very important expression, and maybe in future we will going to use this. So, I just want to show that the delta function can also be represented in different way. So, this is also an identity of delta function that we will going to see a useful relation, and that we will going to use in the future class. So, with that note, I do not have much of time today. So, with that note, let me conclude. So, thank you very much for your attention. See you in the next class.